Alright, this video is going to cover potential energy, but in order to talk about that, I want to recap what work is. Remember, work is a action that causes change or transfer, and it's a force for a certain displacement. And we can talk about all forms of energy in terms of work. For example, with kinetic energy, so since we have work energy theorem, we can define kinetic energy as the work required to accelerate an object from rest to some speed. So when we write 1/2 mv squared, we're saying that this is the speed with respect to the at rest position, or at rest state. Now, when it comes to potential energies, you need more than one object in your system to have them. And the reason being, I want you to consider, say, if we have a book, here's our book, and maybe we are lifting it with our hands. The normal force from our hand is going to do work to lift the book. And at the same time, gravity is going to work against us. So what we have is a scenario where the work we're doing doesn't necessarily translate into more speed. Because if we are pushing with the same force that gravity is pulling down with, that book wouldn't gain speed. So it's not gaining kinetic energy yet. As we saw with the experiment that Du Châtelet re-implemented, the higher position causes more work. Like if I take a bowling ball and place it 1 inch above the tile, my wife might be a little scared when it strikes the kitchen floor. But if I take a bowling ball and place it, maybe 6 feet in the air and then drop it, we both might start to worry because it could do more damage. So something about lifting the book allows it to do more energy or to do more work, even though it's not gaining speed. So we have to consider here that there might be some other form of energy besides kinetic. Well, if we think of the work we're doing against gravity to lift it, then perhaps that's where the energy is. So it's not going into the speed, it's going into that gravitational field. And so we can talk about what we call gravitational potential energy. So gravitational potential energy. And that is the work required, or we can think of it as the work required to lift that object from some zero height to some new height. So work would be against gravity times our change in height. So we get the weight of the object times the change in height. is the gravitational potential energy. We have to be careful here when we include it in our calculations. It's either as work done against gravity or it's gravitational potential energy. We're not going to include it twice. We'll be our bookkeeping will be off. And it's got some conventions. Typically, for objects near the surface, we say the surface is 0 height. Surface of the Earth, sorry. We say the height is 0 at the surface and everything above that is positive. If we're talking big distances, infinitely away is considered 0 and everything else is considered negative work. Since gravity is an attractive force, any object, any like test mass that we put here would be attracted to the Earth. So to hold it at this position, we would actually be doing some negative work because it would naturally want to go this way. Another way to look at 0 being infinitely far away. So let's say this distance is infinitely far away. We have another formula for the gravitational force on an object. And our height would also be r. So we get gravitational constant times the mass of the planet over our test mass divided by their distance. And you'll notice as the distance approaches infinity, this fraction would get awful close to 0. And so we say infinitely far away is 0. Everything else is negative. So typically put a negative in front of here. One question some students have is which object is storing this gravitational potential energy? Are they splitting it equally? What's going on there? It may be better to view the energy as being stored in the gravitational field between them. So neither one really has that energy, and that way you don't really double dip, because in this example that I'm about to give you, we want to make sure that we're not double dipping. So imagine we have 3 masses. Maybe these are, this one is r away, r, and r. If we want to talk about the gravitational potential energy in the whole system, we would find 3 different expressions. We would need to find the expression for the top pair, which is g2m squared over r. We need an expression for the right here, g6m squared over r, and expression for the left pair. Because the potential energy exists between them. So this pair here has an energy of 2. This one has an energy, or this pair has an energy of 6. This pair has an energy of 3. So our entire system would have an energy of 11 gravitational constant m squared over r. We wouldn't say that each one of those masses has this much energy. It'd be kind of weird for one object to have 2 different kinds of energies. So this is why we kind of think of the energy as being stored in the field for this system.